So welcome back, guys. So in this lecture, we'll deal about types of restriking voltage. As you all know that after R extinction, the circuit breaker contacts opens and will form a restriking voltage. So up to now, what the model we did is we took a generator. After that, we have a bus bar and the step-up transformer, and we consider fault occurs here. Okay, up to now we discussed about this concept only. So the fault occurs, the circuit breaker contacts opens. For this we derived about the expression for restriking voltage and all. So now what I want to deal is the types of restriking voltage. So we have two types of restriking voltages. That is, one is single frequency restriking voltage. So what is single frequency restriking voltage means? For this type of circuit only, we model the circuit into to equivalent circuit of that system into such small circuit like this. Okay, we model this and we find the fault occurred here, and we find for this model we find the open circuit voltage here capacitor, which is restriking voltage. In this, if you observe carefully, we have one L component and one C component. So only one frequency is taking place, that is this frequency. So when this only one and C components are there that are oscillating at that transient case, it is called one frequency, where the frequency we given as 1 by 2 pi into root LC. This is what for that model, a simple model to update to explain the circuit breaker operation, we did that. Now coming to this is the second type is double frequency restriking voltage. So in general, the power system is huge, larger. So always we don't have the condition that here the fault occur. So the fault may occur in any between of the lines. So in that cases, we'll have different frequencies taking place between the circuit breaker. That means, for example, if a fault occurs in middle of the line, where the situation is we have two frequency components modeled in the form of a circuit like this. If a circuit like this goes on, for example, a fault occurred here. Now what happens here is, this fault will be acting by both the two frequencies, that is C, LC, LC in this contact. Okay. Now for this fault, the circuit breaker need to experience the frequencies of both two LC components. That's why it is called having two frequencies, F1 and F2. So the impact will be higher than this impact. The circuit breaker need to operate more precisely when compared to this type. So in this different model, like this, we have two frequencies here, that is called two double frequency restriking voltage. Here the circuit breaker need to operate for these two frequencies, where you will getting the restriking voltage in the form of this is about one frequency, and there will be a recovery voltage and legal frequency. So two frequencies will be absorbed by the restriking voltage. That is why it is called a double frequency restriking voltage. So the circuit breaker will protect open because of these two frequencies. Okay. This is about the types of restriking voltage. And now we will derive after complete observation of restriking voltage. We divided first the restriking voltage. For the restriking voltage, we discussed the expression for restriking voltage. That is Vc of P equal to Vm into 1 minus cos omega t. And then we derived the maximum restriking voltage. Maximum restriking voltage, which is given by 2 times of supply voltage. And then we obtained the current time when the restriking voltage gets maximum. That is the restriking voltage, which is in the form of like this, and we obtained the maximum voltage, that is 2 Vm at a time t equal to pi root LC. So obtain this by how? By making this value -1, we got t equal to pi root LC, that is time to reach, that is time to reach maximum restriking voltage. So this is given by t equal to pi into root LC. Okay. This value will be in the form of microseconds, and this is in the form of kilovolts. And then after that we derived a maximum rate of rise of. So we derived a maximum rate of rise of restriking voltage as omega n Vm, which is given by kilowatt per microsecond. So these are the expressions we did for restriking voltage. So other than that, we can't get more than that. For this also we got the maximum, at what time the maximum rate of recovery voltage is also divided by pi root LC by 2. Okay. Now we'll go to the recovery voltage. What about the recovery voltage after the R got extinction? So we'll do that. We'll discuss something on recovery voltage. So expression for recovery voltage of a three-phase system. Expression for recovery voltage for a three-phase system. Okay. As you all know that the RMS value, if you take V of the system, line system, the maximum value we have V max equal to root 2V. Since VRM is equal to what? V max by root 2. Okay. Now, if you take the system voltage as V max sin phi, then the recovery voltage by default was taken by K1, K2, K3, Vm sin phi. Okay, this is the K1, K2, K3, Vm sin phi. This is the expression for recovery voltage. So, why this expression came? To many researchers, they found K1, K2, K3 constants. That means after recovery restriking voltage, all of a sudden system won't get normal. So we'll have some glitch in that. So that the glitches is called the constants we have here. So the K1 is called what is the K1 is called? Demagnetizing factor. Demagnetization factor, which is by which it is the recovery voltage due to which the recovery voltage which is obtained is less than system voltage. So the recovery voltage will be less than system voltage due to the demagnetizing factor. This is K1 equal to recovery voltage by system voltage. So in general, while solving problems, we take K1 either 0.9 or 0.95. We'll solve the numericals in the next class. And then K2 is called condition factor or phase factor. Or phase factor. So in the condition, if the fault occur due to when a fault is grounded, if the fault is grounded, then K2, in that K2 recovery voltage, finding the recovery voltage, if the fault is grounded, we take K2 equal to 1. If the fault is not grounded, we will take K2 equal to 1. If the fault is grounded, we will take K2 equal to 1.5. Okay, these are default values which were already prescribed. For finding the recovery voltage, if the fault is grounded, if not grounded means we will take 1. If it is grounded means we will take 1.5. And K3 is another constant where if you want to find the recovery voltage in line means one phase to neutral means in phase to neutral. In single phase means we'll take it as a 1. If you take the 3 phase, we'll take it is as a root 3. So while following all these things, we have to do. As we all know that after giving a system in a 3 phase, we'll convert into a single phase. After converting into single phase, we'll find the recovery voltage in maximum. If it is asked means we'll find for 3 phase. If it is not asked means we'll find everything in single phase. So the value of K3, if it is asked for a single phase means we'll take 1. We'll ask for K for 3 phase means we'll take root 3. So this is about the recovery rate, recovery voltage expression. So now we'll solve a few numericals where we have for this which is taken from one of the competitive exam IAS. So this is a single phase equivalent circuit for studying the recovery voltage. This is a single phase recovery voltage, single phase circuit for finding recovery voltage which is given, and he is asking to compute the average value of rate of rise of restriking voltage. So the value of rate of rise, average value of rate of rise of recovery voltage, which is given by 2 into multiple of factor of 2 into maximum value by duration. So the first duration means first half of the duration is t equal to pi root LC. So the t equal to pi root LC, which is given by the time to reach the maximum value. So by dividing multiple of 2, that is maximum value of the system, by time duration, we will get the average value of rate of rise of recovery voltage. This is the expression for that. Now what is the maximum value for this signal? This is the signal, which single phase signal, which is given by 11,000 into cos 311. So the frequency is 314. So the maximum value of that signal is, you can write as 11,000 volts, and the rate of rise of recovery voltage is directly given by average rate of rise of recovery voltage equal to 2 into Vm by T. So the T is given by 2 into Vm by T means pi into root LC. So this gives 2 into, so substitute the value of Vm, that is 11,000 divided by pi into the value of inductance is 1 millihenry, that is 10 power minus 3 into capacitance is 400 picofarad, that is 10 into minus 12. After solving this expression, we get 11,072 volts per microsecond. Okay. So ultimately the time t is in, already I said this will be microsecond. So the value of this numerical is volts. So this is the expression, this is the value of average rate of recovery voltage. The second numerical, we have in a short circuit test on circuit breaker. So the following data is appeared on a frequency transient. So at the point of arc extinction, that is given as time to reach the peak restriking voltage. That is restriking voltage, which is given by like this. So the time to reach restriking voltage is 55 microseconds, and then the peak restriking voltage, which is sorry, this is the peak restriking voltage is 100 kV. So peak restriking voltage is 100 kV. Okay. So he is asking to find natural frequency and average rate of rise of restriking voltage. So here, as you know, the time to reach restriking voltage, that is time to reach restriking voltage is what? Pi into root LC. But for finding the natural frequency which is 1 to 0.9 Hz, we have F1 equal to 1 by 2 pi into root LC. So substitute simply the time t equal to here, that is 1 by 2 into t. So example. So here 1 by 2 into the time to reach the maximum restriking voltage is 55 microsecond. So after solving this, we obtain a value of 9090.9 Hz or 9.09 kilohertz. This is the natural frequency of the arc extinction point. So it is up to, we also know that for single frequency, it is the natural frequency vary from 1 kilohertz to 10 kilohertz. it is up to 9.0 means it is optimum value we obtained. And then this is about the natural frequency we found here. And another other thing is average rate of restriking voltage. So I already said that average rate of restriking recovery voltage equal to 2 into the maximum value, the Vm system voltage by time to reach a maximum rate of maximum value. So already know that 2 into Vm is maximum peak restriking voltage. We have peak restriking voltage as 2 into Vm. So already the 2 peak recovery voltage is given at 100 kV. This is equal to 2 Vm. So simply substitute this value here. We will get 100 kV by the time it is taking is 55 microhertz. So simply after solving this, so we will get the value equal to 1.81 kilovolts per microsecond. So this is the average rate of rise of restriking voltage for this system.